was traveling yesterday, and I went through Denver, and it was a blizzard. So my flight got delayed, and I got sick. So we'll see how today goes. So keep your expectations low. So we're going to have two data analysis lectures today. Any questions before we get started?
I just have some problems like figuring out the right syntax with data frames. Like I wanted to have my data frame with a column of pre-informed values, right? And I wanted to add a new column that was that column converted to air quality index. And so I figured out the right syntax to like take a column and like add it or multiply it or subtract it and put it in a new column. So when I tried to do that column as a formula, like using the air quality index library to convert it into like air quality index numbers, it wouldn't work. I forget they are. I'd have to try it again.
So you did something like, so I would do something like, I would probably do something like that. Is that more or less what you tried?
Yeah, I was trying, the air quality index formula takes like a 3.5 value as one of the parameters. So I was trying to plug in like frame of like old parameters, and that didn't work.
So probably the issue, the air quality function doesn't know anything about a series, so one row would be a series. So the air quality function doesn't know anything about that. So the map takes a function that doesn't know anything about it, and basically has a for loop that goes through each one. So some functions, like the NumPy functions, are kind of like list aware, and so you can pass the list and it'll process it. For things that don't know about it, use map, and it'll apply that function to everything. Have you used map before? So map is it's like a functional programming kind of building block. And it's just a for loop, so it's basically for each thing in the loop, apply this function and give you back the result. So it transforms one list-like thing into another list-like thing. Other questions? How are people liking the tools we're using so far?
It's docs.
Yeah, the kind of documentation overload, I feel you. It's maybe too flexible.
It's like the most painful doc reading I think I've done.
So that's good because there's much worse out there. Other thoughts?
I do like how you can see your results pretty much instantaneously. I mean, I guess from like cell to cell.
Yeah. But people do this, like this is.
But like data scientists, right?
Yeah.
He's like, I'm gonna give you something first.
But like a lot of companies have people doing this type of data analysis. Jupyter, you can plug in different languages. There's a language called R, which is what the pandas library is, kind of a Python reimplementation of the basic R data type. There's C++ kernels, so you can write C++ in Jupyter. So it's pretty popular. All right, any other questions, thoughts before we get going?
When you get an error in Jupyter, I find those to be not helpful.
Like the stack traces, like
yeah. Any insight there?
Other
than plug and show?
So generally, anytime you get a stack trace, the middle of it doesn't tell you very much. And so you want to look at either the beginning of it or the end of it. I try to find my code. A kind of primitive debugging thing I do. If I have like a long expression, I'll chop off like method calls at the end and like print the first part of it to see what the data type is, and then try to add one thing. So that could be helpful. But yeah, it's
I mean, it basically just tells you what line went wrong.
Yeah, I mean, there is some more context there, like it'll tell you like what, it'll say like expected this type, got this type, so it tells you that pretty often. But yeah, it's a bit incomprehensible, and the more you use it, the more you recognize stuff, but yeah, it's a pain. Okay. So the next homework, I'll post either this afternoon or tomorrow. It's not already up. We'll do it next week. So today we're going to talk about a use of statistics for making decisions about data or understanding our data. A topic called hypothesis testing. In some sense, this is kind of like the real traditional scientific method in a very particular sense. Our goal with hypothesis testing is to disprove wrong hypotheses. Okay, so if you are like a purist about the scientific method, you know that basically we can never prove that we're right about something. It's no matter what experiment we run, it doesn't tell us, yes, our hypothesis was correct. It can only tell us, no, our hypothesis was not correct. Okay. So that's our idea, is we have something we believe to be true about the data, and we want to basically see if we can disprove our hypothesis. So for common cases in data science, our hypothesis is our data came from a particular probability distribution. So our data, we can think of, we have a bunch of samples from this probability distribution. We could think of our data, maybe we collected the number of, we have a number of heads and tails, and we assume that we have a fair coin, so our probability distribution would be which distribution would tell us about coin flips. Bernoulli, right? So we have data that is sampled from a Bernoulli distribution, right? We assume like this is where our data came from, and that's our hypothesis. Right? And what we're going to do is we're going to see how likely was it that we would get the samples that we got if they really came from this distribution. Okay. If the probability of getting those samples that we got is extremely low, then probably our hypothesis is wrong and our data actually came from a different distribution. Okay? So imagine, so my hypothesis says my data came from this distribution, right? My data points look like this. It's probably my hypothesis about what the distribution looked like was wrong. So that's all we're doing here, and we're going to do it in a pretty formal way. Does that kind of basic idea make sense? We're just kind of seeing, does our data match the shape of the probability distribution that we expect to see? So a really important note here is that let's assume my data looks something like this. Does this mean that does this allow me to conclude that, yes, this is the probability distribution that my data came from? No. Okay. So there are many different probability distributions that could have reasonably generated the data that I saw. Okay. So I can't say, yes, my hypothesis was correct. I I can say, no, my hypothesis was wrong. As an example here, it would be perfectly reasonable to have my data have come from, this distribution that was skewed slightly over. I could have totally had data that was skewed just a little bit over, right? So this is not the only reasonable distribution that my data could come from, right? I can only tell if it was unreasonable. The process we follow is we formulate a hypothesis. Right? We measure our data. And then we compute the probability of sampling data as extreme as the data that we measured from our hypothesized distribution. So you can basically compute something you compute the probability of getting data that is this extreme from our hypothesized probability distribution. If it is extremely unlikely to get data like this out of our probability distribution, we can conclude that our hypothesis was incorrect. So this is, we are pretty limited in what we can do with this hypothesis testing. To do sort of more general, I would say more intuitive analysis about the likelihoods of things, such as the probability that our data did come from this distribution, stuff like that. We need to use Bayesian statistics, which is kind of another branch of statistics, which is all about conditional probabilities, so the probability of one thing happening if another thing happens, that kind of stuff. We may talk a little bit more about Bayesian statistics, but if you want kind of a more complete description of the likelihoods, you have to go beyond hypothesis testing and use Bayesian statistics. Right. So that's the gist, right? We're collecting our data, making a hypothesis, and then deciding whether or not our hypothesis could be correct. So there's some lingo here. The hypothesis here that we're attempting to disprove, we call that the Null Hypothesis. So the goal of hypothesis testing is attempting to disprove the Null Hypothesis. For this part, we want to compute the probability of our data given our distribution. Usually what we do there is we compute a statistic. Okay, so we do things like we look at the mean of our data and the standard deviation of our data, and compare that to the mean and the standard deviation of the hypothesis. We run it through some formula, and basically we assume the output of that formula comes from like a normal distribution, and then if the output is way on the outsides of the normal distribution, we think it's low probability. I think it'll make some more sense when we do examples. But basically, we run our data through some statistic, and we assume that the output that we get comes from another simpler distribution, and that tells us the likelihood of it happening. We compute the probability that we could collect data like this. right? And then when we have to make the binary decision, like, is our hypothesis wrong or not? So we have to pick some cutoff. We say if it's less than this likely to achieve our data, then we will say our hypothesis was wrong. So we call that the p-value. And so basically the p-value is the cutoff where we say this data was so improbable that we're going to conclude that our hypothesis was wrong. So if this is the probability of our data if hypothesis is true. Usually, we are looking at some sort of distribution like this, and we compute our statistic and kind of look at how it compares to the distribution. And our p-values basically tell us where the cutoffs are for whether or not we consider our hypothesis to be false or maybe true. Okay? So if I compute my statistic and I'm out here, I'm going to say, oh, this is really, really unlikely that I would have gotten this data if my hypothesis was true. So we're going to conclude that it's false. If I'm in here, say, oh, it's kind of likely that it would have happened. And so I could say maybe my hypothesis is true. So the p-value controls basically these cutoffs. Okay. It's important not to it's important to choose these p-values first. So another interpretation of the p-value is basically the probability that you are rejecting the hypothesis when it's actually true. Okay. So if I say there's a 5% chance of getting this data if my hypothesis is true, then if I say my hypothesis is wrong, then there's like a 5% chance that I made a bad conclusion. So that's another interpretation of the p-value. We want to set these ahead of time so we're not doing what's called p-hacking, which is basically trying to make the data fit your conclusions that you have ahead of time. Right? You want to choose this value before you run your tests, and so you can kind of remove a little bit of your personal bias from the equation. So typical values for the cutoff p-values are 5% or 1% are pretty common. So if the data I got would only come up 1 out of 100 times, then probably I didn't get lucky, and probably my data came from a different distribution. So that's basically the gist of it. We'll run through some examples to kind of to see how it works in practice, and it'll make a little bit more sense then, I think. Any questions before we jump into examples? How many people have done this in a statistics class before? Yeah, I think it takes a couple of times to everything about it just seems really backwards, right? Because we can't prove ourselves correct. So I think it's really important to get the purpose of here is to conclude when we are wrong. Yeah.
Right. I was about to just kind of clarify. So the reason why we even think about the null hypothesis is that because we can't necessarily prove this is correct. So
yep.
We can just disprove the thing that is the opposite of
there are an infinite number of distributions which could reasonably generate this data that we see here. And so we can't be sure that we found the right one. But we can be pretty sure that, if I thought my distribution looked like this, then I can be pretty sure in concluding that this is not what generated this data. Okay? And there's a risk. I'm making a risk because probability is random. So yeah, this data could have come from this distribution. I could have gotten very lucky or unlucky, depending on how you look at it, right? But so by by choosing my p-value, I'm kind of balancing my ability to actually make any conclusions versus my risk of being wrong. Okay? So if I set my p-value to be 10 to the minus 10, then a lot of time I'm going to not be able to conclude anything from my tests. Right? I'll have a p-value that is 10 to the minus 5, which is very small, but I say, no, I need to be really, really, really sure before I reject this hypothesis. Right? If I set my p-value to 50, then I'm going to make a lot of conclusions, and they're going to be wrong about half the time. So I have to balance my my certainty of my desire to make decisions versus my risk of making mistakes. All right. So we'll start with a simple example. We'll do the Bernoulli or the coin flip example. So let's say I flip. I want to flip a bunch of coins. Let's say I have n equals 1,000 coin flips, and I get 550 heads. Okay. So I'm dealing with a coin. What hypothesis might I be trying to prove, or what hypothesis might I want to disprove when I'm flipping coins? Yeah, I want to know, is this coin rigged? So if it were rigged, what is a hypothesis I could pose that if shown to be false would allow me to conclude that the coin was rigged? That makes sense. So there's kind of an extra step of logic we have to add when we're setting up these hypothesis tests.
So if it's false, then the coin is rigged?
Yes.
You would say a normal distribution where the mean or median is 500 each.
So what kind of probability distribution do we expect this coin to have? Bernoulli, and if we're counting the total number of heads, we could consider it to be binomial. Right? So we're talking about Bernoulli or binomial distributions here. Right? So what if we, what's kind of the opposite of the coin being rigged for one of those distributions? So we have a coin, so we will have a Bernoulli distribution, right? We can flip it and we get heads or tails, right? And we assume that there's a fixed probability of either. Right? So what would it mean for the coin to be not rigged? So for the Bernoulli distribution, there's only one thing we only have one knob we can tune. What's our knob for the Bernoulli distribution? P, the probability of heads, right? So we'll go kind of backwards. So we want to show that the coin is rigged. What would our hypothesis be if the coin was not rigged? So P is 0.5 would be a hypothesis that the coin is not rigged. Does that make sense? So confusing, I know, but so we'll say our hypothesis P equals 0.5, right? The coin is not rigged. Okay. Does that make sense? So we measure, we get 550 heads, right? So now we want to know basically how reasonable or how often are we expecting to get this many heads if the coin really is a fair coin. So how could I figure out basically the probability of getting this number assuming a fair coin? Any thoughts on that? So what distribution is going to sort of describe the number of heads I get out of 1,000 trials? This is the binomial distribution. Right, binomial distribution for 1,000 looks starting to look pretty steep. Right, so this would be binomial of 0.5 to 1,000. Right. And so when we're doing these hypothesis tests, very often we want to know, like, we don't really care about the probability of a particular value. We care about the probability of a value as extreme as this particular value. Okay. And so depending on the problem, the way you describe that might vary. But for this case, I think it's reasonable to say, so this is my data. I would say something as extreme would be anything there or anything there. That kind of makes sense. So I want to add up all of the stuff out here, the probability of getting anything out here, right? And that's going to tell me how likely it is to be as extreme as 550, right? So, so I want to know the probability of getting between 0 and my data flips and data and flips. If that makes sense. So for this particular example, I guess my data would be over here because I had 550 the peak here. That's that n over 2. So depending on the problem, it might make sense to only consider this region over here, or it might make sense to consider both. Right? It kind of depends on whether you're concerned about extremeness in one direction or both directions. Okay. So let's say I'm interested in how likely is it that I am this far away from the mean or further. Does that make sense? This is what the binomial distribution looks like. The idea is how I can actually compute this. Like when I go to Python to try to figure this out, I kind of want to figure out the area here and the area here. So what was the function that tells me about the area? The integral, so we took the integral of this, and you remember what that was called? The PDF. So the PDF, the probability density function, tells me basically the area up to some point. Right? So because this particular one is symmetric, I can basically look at this part and double it to get my answer. Does that make sense? Cool. So how do I get this area out of my PDF? Yeah.
Just a question.
Yeah.
I think there is also the probability match function that dealt with the discrete value. Why are we using the density function here?
This actually is the PMF because the Bernoulli is a discrete, or sorry, the binomial is a discrete distribution, right? Because I can only get a whole number of coins. So I'm drawing it as a curve, but really it is like a step thing. Step functions are really easy to integrate, so I'm still going to use the same techniques work, so I'm still integrating under that, but yeah.
So can you repeat the first one? Sorry.
So I want to figure out this area, because if I double it, then I get the thing I'm interested in. Because this area is the same as this area. So the CDF tells me the area from infinity up to a particular spot. Can I use that to tell me about this?
Just subtract. There's two ways.
Subtract what?
It's one, just everything up to here.
So the area of the whole thing is going to be 1, right? If I subtract off this part, what I'm left with is this part.
No, so that's symmetric, so everything left side is equal to the right side. So
I could also figure out what the point would be over here. So if I found the difference from here to the mean, subtracted that off, and I could just do PDF of this side, and they should give me the same thing. So this here, I know that the integral of the whole thing, the area under everything is 1. So this part is 1 minus whatever on the left of that. Does that make sense? Okay. And then, because I'm interested in measuring whether or not it's as extreme, I'm just going to double this to count for this area too. Okay. So this tells me basically the probability of getting this many heads away from the mean. And that's going to basically tell me, can I assume that my hypothesis was correct or not? Does that make sense to everybody? So what do we, any guesses what this p-value is? Pretty low. How low do we think? 0.05? Any other guesses? So the p-value we get here is actually about 0.001. So this is about a 0.1% chance of getting this many heads. We should have set these ahead of time, but you know, for reasonable cutoff p-values that we could have chosen of 5% or 1%, we could conclude that our hypothesis was wrong. And so what does that tell us about our coin? Not a fair coin. So we have about a 1/10 of 1% chance of making an erroneous conclusion, but we can reasonably conclude that this is not a fair coin. If we had gotten 500 heads, would that have told us that this is a fair coin? No, right? If we had a 60-40 coin, like, you know, we could have gotten 5 heads, or one, you know, or a 51-49 coin. It would have been totally reasonable to get 500 heads, right? So there's a bunch of different distributions that could have given us, you know, with reasonable probability, 500 heads, right? So just because we're in the middle of this distribution does not mean it's the right distribution. Okay? But if we're way outside of it, it probably means we're the wrong one. Does that make things a little more clear seeing an example? Okay. So very often we're interested in, we have a sample mean and a sample standard deviation and a hypothesized mean and standard deviation. We choose a test to run. I usually look at the Wikipedia page. There's a list of all these hypothesis tests, statistical tests. You kind of read what they're used for the use case. You find the one that seems right. You run it through the formula. It gives you a value and says, this value, if your hypothesis is true, comes from a normal distribution, mean 0, standard deviation 1, whatever. Okay. And so if you get something close to 0, it means you can't disprove it. If you get something really big or really small, it means probably it means you can disprove your hypothesis. So that's kind of the standard workflow. So we'll now let's go to the notebooks and we'll take a look at a few examples.
So then,
Yep.
with this class, I don't want you guys to ask how much math you want us to know. But since we're doing a lot of programming as well, like how much time do you want us to be spending on like math core principles?
So you'll have homeworks doing this. I'll basically say, run this test and tell me whether or not you can reject the hypothesis. So you'll basically just be going through a formula, and you have to understand how to compute and use a p-value. Is kind of the amount of math you need for this part. Here we have that coin example. So if I had 100, or I have 1,000 coin flips, 550 heads. This is my PDF, or sorry, the CDF. Did I say PDF on the board? Oops. I meant CDF. Sorry. So yeah, the CDF tells us the area. My bad that I misspoke. So I'm just going to compute the CDF of my data, doing 1 minus that multiplied by 2.
What does CDF stand for?
Continuous distribution. Or sorry, cumulative. So that's the area from negative infinity up to where we're at. So this part here tells me basically the probability of getting more than 550 heads. When I double it, I get the probability of being basically 50 away from the mean. Yeah. So I picked 1,000 and 550. What do you think would happen if I picked 155? What? So the p-value is going to get smaller?
Yeah, I like that.
I think it would get larger. Why would it get larger?
Well, you have small sample size, it's high.
So with a smaller sample size, there's more variability, right? So getting 500 extra heads is kind of a much bigger proposition than getting 5 extra heads. Okay? So if I have a really small sample size, my p-value is now 27%, which means there is a 27% chance of getting, an extra 5 heads or tails from a fair coin. Okay? Does that kind of make sense? So I can't make any conclusions if I only have 100 coin flips. Right? So I'm going to do a little bit of p-hacking here. So this would not be sort of rigorous analysis, but how high do you think we'd have to go here before we get to a number of heads that would be like significant with only 100 samples? So how many heads do you think we have to get before we could conclude that our coin is not fair to say like a 1% p-value with only 100 samples? 80? I think that's too many. So with 80, we can be confident to 10 to the minus 10, so that's extremely confident. 60? 60, we're about there. So between 59 and 60 coin heads, we can be pretty sure that we had well, this is only 5%, so maybe. Like 62, 63 heads, we could say pretty definitively that we had an unfair coin, even if we only flip it 100 times. Okay. So again, this is like not scientific and it's bad. It's more just kind of a thought experiment about how skewed our data has to be to make confident decisions with small sample sizes. Curious with 10 if we ever so we need, if we only flipped it 10 times, we'd need about 8 out of those 10 to be heads. Okay. So what if we bump this up? So we have 1,000, and now we have, an extra 5% heads. What do you think the p-values can look like here? Oh wait, we already did this one. If I bump this up to 10,000, add some more zeros here. P-value is going to get really small. We're already at, this is like machine precision. Okay. So for all of these, we had 5% extra heads. Okay. As n got bigger, really, really quickly, getting 5% extra became a pretty clear indicator that the coin was not fair. Does that make sense? So let's play around with this and plot this. So let's take let's go from like n equals 1 to let's say 50,000. So the really nice thing about working in Jupyter, I'm not like entirely sure if that last line worked. And so maybe I'll just look at the first 5 numbers to see. So we're going to go up by like thousands. Cool. And then the y value, let's compute. Maybe, so we're going to have an extra 5% heads. And trying to think of when I should cast this to int. I'm at the point where I think a lot of you were, where I know what I want to do, I don't know the magic words. A useful thing here, the dir command tells you all of the methods of an object, all the properties of an object. So this is going to list all the things. And I don't know any of these. There's a real. Real, I think that's for complex numbers. I can round it. Let's try that. Success. So we'll make a new array with ints. Okay, and then we'll plot this p-value for n. So we're just going to plot x versus here. So there's a one-liner to do this, but we're going to use a loop here. So we'll just do. Everybody see what I'm just bringing up here? Oh. There we go. Okay, so now we can finally plot. So we don't get a particularly interesting graph here because if you remember my first x, I went from 1 to 1,000 very quickly. So maybe let's change our range a little bit. Not very interesting. Anybody see what I'm doing wrong here? Try this a different way. Well, I will look at this after class. That's a bummer. Okay. Well, so I have some other examples that are already written, so I don't need to worry about screwing them up. So, So here's that same coin flip example. This is what the PMF for the binomial, or the PMF for the binomial distribution. This is where our data is on that for 550, so you can see it's pretty far outside. Another kind of useful thing that helps us do these hypothesis tests is called the central limit theorem. And the idea is basically if we add up random variables, we add up enough of them, it doesn't really matter what they look like. They turn into a normal distribution, or a Gaussian distribution, once I add up enough. Okay? So if I add up enough, I get a mean of n times the mean of the original. So that kind of makes sense, right? If I add up enough things, and the mean is going to be kind of the mean of those things, and then the variance actually squares with the variance, but it becomes a normal shape. So no matter what distribution I take, if I add up a bunch, I get the bell curve out. If I take enough things, that's actually one of the ways to derive the normal distribution is to think about adding up infinitely many of these things, and what shape do you get. So it's kind of interesting. It's useful for us because when we have a lot of data, we can kind of assume that we're going to get a normal shape out, kind of no matter what the data looks like, which is pretty cool. What we have here is a plot of, this is the normal distribution that we expect from the central limit theorem. And this is coin flips. And we see that it matches pretty well, even for a relatively small number. So here we have 10,000 coin flips. You see it already looks a lot like a Gaussian. And so we'll use the central limit theorem to basically assume that we can assume that our distribution is Gaussian, even if the data itself is not really Gaussian, as long as we have enough of it. So here we have another example. So basically, we want to determine whether or not the freshman 15 is the thing. Okay, so freshman 15 says that on average people gain 15 pounds their freshman year. I went to a school with really, really terrible cafeteria food, so I think I did not, but depending on where you go, maybe that's the thing. So what we're going to assume, right, is that the average weight gain is greater than 15 pounds. Okay, that's going to be our hypothesis. Right? If we prove that wrong, then we can say that the null hypothesis is wrong and the freshman 15 is not a thing. Okay, so we're going to set our experiment up so that we can disprove the freshman 15. And we'll say we want a 1% significance level. So if we get a p-value that's less than 1, then less than 0.01, we'll say our hypothesis was wrong. Okay? So we want to be very sure whether or not our assumptions, our conclusions about freshman weight gain are correct. Okay. So we're going to get n students. We're going to sample them. And so we have 137 students. We see that on average they gained 2 pounds, 2.5 pounds. Here's the standard deviation. Okay. And so we look at Wikipedia. And here's the statistical hypothesis test page. And there's not a table. We look at the test statistic page. So here's here's like a list of statistics you might compute and when you would want to use them. And so depending on what you know about your population, what you know about your distribution. So here we're using the one sample t-test. And so there's this formula T. We look at the difference between our hypothesized mean and the sample mean, right? And then we divide by this by our standard deviation. Okay. So in this case, we don't know anything about what we don't have a hypothesized standard deviation. So we are hypothesizing that freshmen gain a lot of weight, but we have no idea like whether it's a really wide tail or if everybody gains exactly 15 pounds. So we're not including that in our statistic. But we do know the variance in our data. Right? So if we have a really big standard deviation, then our conclusions are going to be a little bit less certain, right? Because there's a lot of variance, so our sample might not be representative. And then we also, the sample size is in here, right? The more samples we have, the more confident we have that this is, that we really understand the population, right? So that's kind of what goes in this statistic. But it's just some formula we plug and chug, right? That gives us this t value. Okay. The t value comes from this Gaussian distribution, right? So we basically just look at where our t value falls in this Gaussian distribution, and if it's way on the edges, then we can reject our null hypothesis. If it's in the middle, then our hypothesis may be true. Okay. So here we go. So we're going to compute our t statistics. So this is our sample mean. So people gained 2 pounds on average. We hypothesized that they would gain 15. We had this standard deviation, these many people. Okay. And then our p-value, basically we look at the CDF. So we look at basically the area we're looking at the probability of having this little bit of weight gain or less, given our data, okay, and we're computing this. So our t is minus 25, okay. And we're assuming that this t came from a Gaussian distribution centered at 0. Okay. So our mean is 0. Our standard deviation is 1. So if you remember, like 68% falls between -1 and 1. We're at negative 25. Right? We're way outside of the predicted range. Okay. And so our p-value is insanely small. So if the freshman 15 were true, right, the chances of us picking a sample of students that gained 2 pounds on average are, 10 to the minus 146. So we can conclude that our hypothesis was indeed incorrect. So does that kind of make sense? So this is kind of the more typical process. We have this statistic that comes from, we look at what we know, what we assume about the population, and then we pick a statistic that's appropriate for whatever it is we're trying to figure out, right? Compute it, and then see where it is. It's usually this t-value that we get, this statistic, is assumed to come from a Gaussian mean 0 normal 1. So this next thing is kind of what I was trying to show before, a little bit different. So basically what we're doing is we are saying like, well, what would our p-value be if the measured weight difference were x? Okay, so And then we're just we're looking at the t-values, or the p-values. So if my sample mean, if my average weight gain is about 10 pounds, that's when I'm starting to be like, okay, maybe the real average is 15. Like maybe I got a little bit unlucky, and you know, went to the skinny dorm or something, right? But and then, you know, if I measure 15, it's pretty likely that my data is correct, right? Or that my hypothesis is correct. But it's about, let's see, so probably at least like 11 or 12 pounds would be where I would, you know, have my cutoff. Yeah. Again, this is p-hacking, right? This is for kind of understanding what would happen depending on our data. You should not, you know, draw these curves and pick the line and adjust your hypothesis so that you, you know, to get the output you run, the result you want. This is just for kind of understanding. So just to run through that again, compute our t statistic. Just look at where it falls in the normal distribution, and indeed very unlikely. Here's another one. We are trying to figure out whether or not there are equal numbers of men and women in the state of Utah. Okay. So our hypothesis is that we have a 50-50 split. So we're assuming that gender comes from basically a coin flip, a fair coin flip. So our null hypothesis is that when you're born, there's a 50% chance of you being a woman. We'll say 5% significance. So we're sampling graduate students in a computer science course. Seems like a good idea, right? So we have, so we just have this this series, the gender, and so this is just an index. Here we are basically converting male and female into 0 and 1. And so now we just get this list of 1s and 0s out. And so this is just a little bit of data wrangling. And from our Wikipedia page, we have decided that the one sample z-test was the one we wanted. And so to compute that, we need to know n, the number of people in the survey, the number of women, the average gender, the mean standard deviation. So we had 17 women out of 62, which was 27%, and there was this much standard deviation. So the z-test, right, we just plug it in. Right, we have our sample mean. We expect the true mean is 0.5. We expect that there's a 50-50 ratio. We have our standard deviation and the number of people. So we compute the z-test, which is -4. Okay. So again, this tells us basically a sample that we picked out of this supposed Gaussian distribution that the z-test is supposed to come from. Right, so again, our z-test statistic is way out here, right? So we have a really low probability. Okay. To get the p-value, to figure out what that probability actually is, we use the CDF, and it's 10 to the -5, which is well below our threshold of 0.05. So only 4 times out of 1,000 would we expect to get a distribution that extreme. So we just proved that Utah is not evenly distributed with men and women. What did we do wrong?
Populations.
Yeah, our population sample was not really representative of the whole state, right? So what we showed was that graduate CS courses probably do not have a 50-50 male-female ratio, which is a conclusion that, having spent a lot of time in graduate computer science courses, sounds true to me. But our sample wasn't representative, right? So we did all the machinery correctly, or we didn't make any coding mistakes or anything like that. We made a mistake interpreting a sample to be representative of a population when it really wasn't. These statistics that we looked at here, we assume that the value we get out is distributed from a Gaussian, or a normal distribution. The normal distribution is pretty tight. As you go further away, the probability decreases really fast. So especially when we have really small data, we kind of expect that we're going to get some values that are pretty far out. So there's this other distribution called the student's T test. It looks kind of like the Gaussian, but the tails are much fatter, which means basically you have to go further out to be more sure that you're like kind of outside of the range. So the student's T test is useful when you're kind of less certain about your data. And so this is we're just going to plot the this is the Gaussian distribution versus the T distribution. So they look pretty similar as you have a lot of samples. They look very similar, but if your sample size is small, you can see that the T distribution is much like longer or thicker tailed. You'll see this when you're choosing your statistic, depending on the number of samples you have. You might use the T distribution instead of the Gaussian to deal with that uncertainty. We do this hypothesis testing. We might make mistakes. The lingo around this is needlessly confusing. These type 1 and type 2 errors, I think, are just really the stupidest names because it doesn't tell you anything about what they mean. So anytime you hear type 1 or type 2, I urge you to just look up whether or not that means false positive or false negative. So there's kind of 4 things that could happen, right? If the null hypothesis were true, we could either conclude that it might be true or that it is false. So if we reject it when it was true, that would be a false positive. If we reject it when it is false, we say it's false and it was false. We did good. We got it right. Right. If we don't reject it and it is true, that's also good. Right. If we don't reject it and it is false, right, then that's a false negative. Basically, all we can do with the hypothesis testing, the p-value tells us the probability of this right here. Okay. So the p-value gives you the probability of getting that data if the hypothesis is true, right? So basically, if you reject it, you have that probability that that data did come from the null hypothesis and you labeled it incorrectly. So that's what the p-value tells you. We'll look at one more example here. Maybe not. Well, there are a couple. If you work in the pharmaceutical industry, Your null hypothesis that you want to reject is my drug doesn't work, right? If you conclude that that null hypothesis is wrong, when in fact it is true, right? You're basically marketing a placebo, right? We would call that a false positive. Right? We're saying there's an effect when there isn't, right? This would never happen in a pharmaceutical company, but maybe they have a drug that's effective and their experiment says that it's not effective for some reason. That would be a false negative. They would never ever do that, right? Certainly they would rig their tests to get the false positive. At trial, another case, right? The null hypothesis is the defendant is innocent. Okay? A false positive would be convicting somebody that is innocent. Right? We're rejecting the null hypothesis when it is in fact true. A false positive or a false negative would be when we don't convict a guilty person. And so I think the hypothesis testing is kind of like I think the trial analogy is good. We're trying to prove beyond reasonable doubt. All we can say as the jury is that the prosecutors did not prove beyond a reasonable doubt. We're not saying that the defendant didn't do it. We're saying that the prosecutors couldn't prove beyond a reasonable doubt that they did it. Right. So p-hacking is when we are kind of trying to massage our test to fit the data. It's bad, don't do it. If you repeat your test a bunch of times until you get a p-value that is where you expect it, right? It will happen, right? The probabilities, if your samples are random, right? Eventually, you should expect that you'll get a p-value that's small enough for your range. That doesn't mean that your hypothesis should be rejected. So if you are repeating your experiments until you get the p-value that you want, right, you're doing it wrong. So I think we'll leave it there for today. Any questions about hypothesis testing? So the next homework, you'll set these up and play with them. It's mostly just plug and chug in the formula, use the CDF to figure out what your p-value is, interpret the result. Cool. Let's go ahead and take like a 5-10 minute break, and then we'll come back and talk about linear regression.
Yeah, masters.
Engineering students?
Yeah. So I figured out what stupid thing I was doing. When I was computing the number of heads, I said the number of heads that we got was 105% of the number of coin flips instead of 55%. So probability of getting 100, of getting more than all of the flipped heads is of course 0, which is why everything's 0. So this is the graph of, so if we have an extra 5% heads, this is a graph of the probability, the p-value plotted against the number of flips. So you can, as you can see, until I get up to 200 some flips, right? Getting an extra 5% heads is not that crazy, and beyond that, it gets to be really low. So I'll post these online. Okay. So switching gears. Next thing we're going to talk about is linear regression. So here, what we're trying to do is trying to make sense of the relationships between different features of our data. Okay. So so this is my data, right? And I wanted to describe this. But the statistical approaches we've talked about so far, maybe one of them would be kind of useful, one or two of them. But what of the descriptive statistics that we discussed might be useful for talking about this data? So like mean, standard deviation, probably not.
Correlation.
Yeah, so correlation or covariance are the two. They're like closely related. They would tell us something about the relationship between x and y. but I think what would make it be easier to understand is if I could summarize my data by saying it's pretty close to this particular line. This is what's called a linear regression. We are fitting a linear function, a line, through our data. And we're going to use that to describe it or to make predictions. So I can describe my data this way. How would I use this to make predictions? So I pick an x, so I want to know what y's I should expect for a particular x. I come over here, and this is my prediction. So this is kind of the simplest model of a predictive model that we could come up with, and it's super useful. It shows up all the time. Today we're going to talk about how to compute this line and then what we can do with it once we've computed it. So how do we, what are kind of the parameters or knobs of this line that we can tweak when we're trying to pick which line should go in? Well, maybe, what's the equation of a line look like? Okay, so we have y equals ax plus b. When we're choosing which line, we have to pick an a and a b that match our data as well as possible. We would obviously like to choose the best possible line. So we need some way of measuring how good our line is with our data, right? So that we can either make it better or conclude that it is the best that we could do. So how might we go about measuring how good of a line? Compared to our values. Yeah, so there's a few different ways we could do that. One thing I do is I could measure the absolute distance to the line. It's maybe a little bit more complicated than we would like. So it's kind of like a simpler, how close am I measure I can do. So this projecting onto the line is too much. I don't really want to have to deal with the x part of the distance, if that makes sense. So I'll just look at the y part. So this part here, this would just be I take my measured value, my sample value, and I just see how close it compares to the expected value from my line equation. So we call this the residual. And it's just basically how far is my y off at a particular point. So one thing we want to try is just say, okay, the residual at each point is the difference between the line and the data point. To pick the best line, what would I do? So this tells me how good I'm doing. I minimize it over what? Over all the points. So one thing I might do is I just say, okay, so the error equals sum of yi minus axi plus b. So the minus And so the best I could do would be an error of what? If I had the perfect line, what would the error be? 0? So let's try to see if we can solve for 0. One way I could solve this equation is to just set A to 0 and B the sum of yi over n. And if you plug this in, you'll see that actually you get an error of 0. Okay, so I stick this in here. I get n of these overall. Subtract off. I get the setting basically b to be the average for yi's. What does this line equation look like? This is a flat line. This is b equals the y mean. Okay. So for this particular way of measuring the error, I get an error of 0, and I get a line that's not very helpful. So what went wrong here?
Where is n coming from?
So n is the number of data points that I have. So this is, I'm just saying, this is the average. And when I sum up, I'll get n y's. Or I'll get n b's. So yeah, what went wrong here? Why didn't this work? Take a second, talk to your neighbor, see if you can spot the problem. So I measured my error this way, and it gave me a bad answer. Yeah.
I don't know.
This is a valid equation. I just set a equal to 0, so like the algebra is all good. It's the way that I formulated what I was doing. So if you plug this into this equation, you will get an error of 0. So, and of course we can't get an error less than 0. So what did I screw up in how I was sort of setting this up? So it has to do with signs. Signs with a G.
Because part is bigger than the minus b, and the part is smaller than the.
So let's think about two pairs of points. So as if I just had these 2 points, with this measure, I have an error of 0.
So one is up, one is down.
Yeah, one is up, one is down. So they cancel, the errors cancel out, right? And so by this way of measuring the error, I basically allow things on the opposite sides of the line to cancel out. This is not the only solution here, right? I could choose my A, I could get another line where everything exactly cancels out. I think there's an infinite number of solutions I could come up with here. But yeah, this is kind of the trivial solution where the slope is 0. Right? And it's because my errors just cancel out. So how do I, and so maybe an issue you could see right now is that the error at a particular point can be negative. So what does it mean to have negative error? That doesn't make any sense.
Use that to value.
So one thing I could try is I could try sticking an absolute value in here. And this is going to give me something a lot more reasonable. So now the error at each point has to be positive, right? And so I'll get a line that's much more reasonable. Okay. Unfortunately, this is a really, really difficult. So if I define my error this way, it becomes really difficult to compute what the best A and B are. Okay. So the way that we compute these is basically we make a guess, and then we adjust our guess just a little bit to make it a little bit better. The way we do that was with calculus, right? But the idea is we tweak our A and our B a little bit based on where we're at so that they're improved. Okay. And this is really hard to do with absolute values because the graph of the absolute value looks like this, right? If I add up a bunch of absolute values together, which is what I'm doing here, my graph looks something like that. Okay. And finding the bottom here, the smallest error, is really, really hard because I have all these jaggy things. So this is sometimes something we like to do. We would call this the L1 minimization, where we're minimizing just the absolute value of the error. But it's really hard to solve because we're basically trying to find the bottom of this jaggy thing, and then it's numerically it's really hard. So absolute value is not good. We want kind of like a smoother version of the absolute value. Any thoughts on how we can get something like absolute value but a little bit smoother? Squared. So instead of taking the absolute value, we square it. Okay. Now we get a nice smooth graph. Okay. And by using calculus, we can actually find the minimum right away. Okay. I think I'll skip the calculus. But basically, we sum this up to find the A and the B that have the smallest error. Right? We take the derivative, set them to 0, and what we come up with is so the bars here mean the mean. So I take my average x and my average y, I do this subtraction, sum them all up. This gives me my A. To get my B, I just subtract off the A times the mean x to get my B. So yeah, don't need to memorize these formulas or anything, but they're pretty straightforward formulas. Right, they just depend on the mean. And these gives us the best possible line where we measure the quality of the line by taking the squared residuals. So this technique is called least squares regression or linear least squares regression. Right? And so this is where the term least squares comes from, or minimizing the squared error. We can compute this for any data. Right, so you give me a set of x and y points. I can compute you the best line. Is that always going to be a useful thing? Probably not. So if my data looks something like this, right, I can fit a line to it, but it is, not going to be very useful. Likewise, I can fit a line to that, but it's not going to be very useful. So we would like some way to kind of understand whether or not this line that we picked describes the data well. And so we could, draw it and rely on humans to visualize it and see. But we'd also like some kind of numeric quantitative way of doing this as well. So how can we kind of measure or describe how good our line is at fitting this data? So what we had picked our A and our B. We have our data. What can we compute or measure? The little RIs we were talking about?
Yeah.
Yeah, so which equation up here talks about those? So this one, right? So one thing we can do is we can just compute the total distance, or the total difference from our estimated or predicted y's from the line, sum them up, right? And that will give us an absolute measure of how good our line fit is. The issue with that is that it's sensitive on to the scale of the data, right? So if I had a data that was pretty close to a line with a little bit of noise, if I just make everything bigger, then my error gets worse, even though the fit is the same, right, just because of the scale. So we actually would love to somehow scale this, or take the scale out, right, and get some sort of scale independent way of measuring this. Okay. So the residual sum of squares is basically this. It's called the residual sum of squares. This is the absolute error in our fit. Okay. To get a relative value, we want to normalize this based on how much variation there is in the data period, right? And then we can get a relative value. So we have this so this tells us basically how far off our line is. The TSS, the total sum of squares, is basically just how much our y varies. So this is a measure of how wrong we are. This is a measure of how much variation there is in our data. So what we compute is something called the R-squared measure, which takes both of these into account, and it's kind of a normalized way of measuring our error. The R-squared is so we can write it out in two ways. Okay. So we're trying to measure basically how much of the total variation in the data can be attributed to basically the line. Okay. So if the line is perfect, and it goes through every single data point exactly, what's my RSS going to be? 0, right? There's no error at all, and the line is perfect, right? So all of the variation of my data is explained by the line. This is basically what this is telling us. So I get a value of 1. If my line is terrible, all right, my RSS is going to be very high. It actually can't be greater than the TSS. Right, so in the worst case, RSS is going to be TSS, in which case I get an R² value of 0. So the R² value is nice because it ranges from 0 to 1. 0 being terrible, 1 being perfect, right? And then in between, it gives us a sense of the quality, how much of the variation of my data is explained by the line. So one way we think about, how good is our line fit, is we look at the R² value. If it's very high, then you could say yes, there appears to be a good linear relationship here. If it's not so high, then we probably have the wrong kind of model. Depending on the data that you have, the high enough R² value has a lot of variation. Okay. If you have, if your data is like social media followers and I don't know, ad clicks or something, right? You're probably happier with a much lower R² value, right? If a line describes some of the relationship between those two things reasonably well, then it's going to be a useful model for you. Right? If your data is some sort of like physics calculation, then you're going to want like a 0.99999 R² value, or probably your physics model is wrong. Right? So depending on kind of the use of this data, whether you and sort of why you expect to see this relationship, the acceptable R² values where you're going to say, yeah, there's a linear relationship here, are going to vary a lot. So, but that's kind of the cheap takeaway is R² close to 1 good, R² close to 0 bad. Cool. So let's go to some code. So I used the letters A and B. We'll talk about tomorrow what happens when you have many variables that you think might be related. Typically, these the coefficients, they get called beta because there might be a whole bunch of them. So this is the A, this is the B, yeah, so it's just a nomenclature difference. So there's a few different built-in tools for doing this. We'll see stats models is probably the most powerful, but the weirdest. And then scikit-learn and SciPy have built-in stuff. In terms of computation, least squares, linear least squares is like the easiest numerically, so it's really, really fast and robust and efficient. So it gets used a lot of places. I think this is the first time we've seen SciPy. It is basically libraries that use NumPy arrays for stuff. So it's like a higher level tool built on NumPy. Stats models is a Python port of an R library. So R is a language for doing statistical analysis. Most of the good stuff from R has been added to Python packages. R is one of my least favorite languages. sklearn is scikit-learn. It's like a machine learning library that's, I don't know if it's part of SciPy or related or what. Cool. So we have this data. We have this advertising data, and it is basically for a bunch of ad campaigns. It says how much people spent on various forms of media and then what their sales were. The one sticking to cool. So we have, so for this campaign, they spent a lot on TV, much less on these two, and then these sales. So this is the data we're working with. So 200 ad campaigns worth of data. So the first thing we might want to do is just try to plot it and figure out what's going on. So this is we're in kind of the exploratory phase. So we'll scatter plot each the TV, radio, newspaper sales versus the TV, radio, newspaper versus sales. So this is the amount of money spent on TV, radio, and newspaper versus sales. Any insights on this that just people get from looking at it that maybe we want to try to confirm or follow up on? What do we see from looking at this?
The more you spend on TV, the more sales.
Okay, so the more you spend on TV, the more sales you tend to get. Does that apply to TV only?
Probably radio.
Radio looks like, yes, spending more on radio gets you more sales. What about newspaper? Newspaper, it looks less conclusive, but maybe. Yeah, hard to say. What do we see about, sort of the relationships between the various media? Do we tell anything about TV versus radio versus newspapers? Radio might be more cost effective. Why do you say that? It looks steeper. So it looks like a smaller increase in ad budget here translates to a bigger increase in sales over here. So that's something that, yeah, seems to be the case from looking at it. We can confirm that if we do some more rigorous analysis. Yeah, I mean, other stuff, people spend a lot more on TV, so TV seems to be a more expensive media to advertise on than the other two. Newspaper seems to be pretty I was going to say it's pretty cheap, but I guess some people are spending more on newspaper than radio, so who knows. If you are working at an ad firm, what information do you want to glean from this? How are you, like, what do you want to use this data to figure out? Yeah, how do you want to spend your money, right? Which of these is the, the best place to spend your ad money? So, yeah. So based on this, we think, okay, maybe we should put all of our money in radio, but let's figure it out. Yeah. So if we look at our data, we get kind of our basic descriptive statistics. So I don't know that any of these are particularly interesting right now. I will note, so here, like, these points, they look like they're from 3 different data sets, but they're the same data. They're just different axes of the same data, right? So this blue point corresponds to some star and some red square, right? Each like triple of these is one data point. So we don't know anything from this about the relationship between those things. Yeah.
You know when this is a year of when this will be done?
I don't know. Yeah, I don't know. So it's from a textbook for this ISLR, which is you can get the PDF free. It's I'll post readings from there occasionally. It goes pretty heavy into the math, and it uses R, not Python. But there's some useful stuff in there if you want some supplemental stuff. And again, yeah, free PDF online. So just Google ISLR, you'll find it. Yeah, I don't know where that came from. Cool. So one thing we could try to do. So at this point, now we can start to figure out numerically what these relationships are. We might just look at doing a linear regression to figure out how these various advertising media compare sales. So here we're going to use this the stats models library to do this. So the SM is the stats models, the OLS is ordinary least squares. The way that you specify the formula is really weird. So you specify it as a string. What we're saying here is that sales is a function of TV, or sales is proportional to TV. Right? Give me a line that fits sales and TV. So yeah, this is very different from any of the other libraries. And then so we fit, and then this tells us about the fit. So our dependent variable is sales, so this is our y value is sales. We're doing an ordinary least squares model. We have our R squared. It tells us some other statistics about all this stuff. This is our R squared value, so 0.6. So if we look at, I think we've plotted this a little bit lower. So these are the values we get out. So the intercept is the B, just the constant that we add. And then the coefficient for the TV tells us the slope of the TV line. So what does this intercept value tell us in terms of this problem? So think about where the intercept shows up on our graph.
At $0.
So if I spend $0 on TV advertising, what does this value tell me? So if I spend $0 on TV advertising, this is the number of sales that I should expect to get. And so this is like my not advertised kind of baseline. Okay. And what does this tell me? This coefficient. So this tells me basically for each $1,000 in TV advertising, how many 1,000 sales should I expect to get? It's a good thing that it's positive. If it were negative, what would that tell me? If this were negative, it would tell me that if I spend more money on TV advertising, I decrease my sales. Okay, so an advertiser doesn't want you to get into that situation. I am curious if there are any ad campaigns where that is the case. Like an ad campaign that is so bad that it actually reduces sales. That would be an interesting data set to find. Would these tell us, these are actually hypothesis tests right here. This is telling me the t-value of this coefficient being 0. Okay, so what it says is, assume if this value was 0, basically what is the probability of getting this? My p-values are tiny, which means that these coefficients, both of these numbers, are very, very highly likely to be non-zero, meaning there is some sort of relationship here. We'll talk more about that tomorrow, but and this is a confidence interval, so this tells me basically what range of slopes and intercepts are kind of likely. Okay. Again, we'll talk more about that, and then some other statistics. But yeah, so for now, right, we see what the coefficients are. We can interpret them a little bit. We get the R-squared value, which tells us there's some relationship here. So for this data set, what do we think about? And so if we look up here, we see this, our R-squared was 0.6. So we can kind of get a feel like, yeah, there's a relationship there. It's not super tight, but there's definitely a relationship. Is that like a useful, do you think the linear relationship we've computed is like a useful thing for us for this particular model? Yeah, I think so, right? I mean, having just kind of an estimate of what goes through there. I think for this data set, it's relatively low coefficient, but it's still like there is a relationship there, and we describe some of it. So, you know, in this case, R value of 0.6, you know, is fine. So if we plot this, okay. So we're going to plot the TV versus sales with points, and then we're going to plot, so this OLS predict function basically takes, we're going to plug in the TV values here, and it's going to draw it as a line, and we show it looks like this. So, yeah, I think we're capturing, there is a relationship here. Our line measures it pretty well, but it's not, you know, super tight, which we kind of expect that, right? We expect there to be a pretty big variability in the amount of money you spend on TV and the sales, right? It depends on the product and the market and the quality of the advertising, all that sort of stuff. Cool. So, yeah, so this says without doing any advertising, we expect to sell 7,000 units because of our coefficient, our B0, our intercept was 7. And the slope says basically this is the ratio of increasing our sales to increasing our TV budget to increasing our sales. And then the SSR is this is the unnormalized values. This is the sum of squared residuals. And then the R squared, we normalize that by the TSS. And that gives us our 0.6. Okay, so we'll do the same thing using the other libraries just to see they look totally different. Okay, so here, so we're just getting our x and y's as columns, and then we're doing this linear regression dot fit. So here we're not specifying a formula or anything. We're just giving the x and the y's, and it has this predict function, which is similar but not the same as this OLS predict function here. And so the APIs are similar but not the same. But you see we get the same line out. There's a relationship between this linear regression and the hypothesis testing. So here our hypothesis that we're interested in is there actually a linear relationship between my variables? Okay. So we fit this line, and we'd like to say, like, does this line mean anything? Like, is there actually any sort of significant relationship? So the R squared value gives us some way of thinking about that. We can also use this hypothesis testing to think about the same problem. Okay. So basically, what we are thinking of is that we're thinking of our betas, our coefficients, as random variables. And if we imagine our data as a sample out of like some distribution, we're kind of interested in like, okay, if we got a new set of data from the same distribution, how much are these lines going to change, right? So these lines form like a distribution. If I got slightly different data, the lines are going to move. How much are they going to change by? What's kind of the range of values for these lines that I can expect? And so the hypotheses we're interested in are basically, or that we might consider, are either that these coefficients are 0 or not 0. Okay, so our null hypothesis is basically the coefficient value should be 0. There is no relationship between, TV advertising and sales. Okay. And if we do detect that there is a relationship, we can, if it's extremely unlikely to get our data with that relationship being 0, then we can say that there is a relationship. So we have this test statistic. We can compute the probability of getting this data without any sort of linear relationship, and the stats models reports that for us. That's the t value and the p value for our coefficient tells us basically what is the likelihood that we would see this data if that coefficient really were 0. Yeah. So here, so we're going to look at some synthetic data. So here we have this. Our data is y equals 3x plus noise. So we're just going to generate this data, and then we're going to fit a bunch of lines to it and kind of see how the lines, how the noise affects the shape of the lines. Okay. And to kind of give you an idea of what we mean by talking about those betas as a distribution. Okay. So there's some, the mean beta that we expect to see here is 3. Right? We expect that the slope is 3. But because there's noise in the data, we're going to get slopes that are kind of around 3, but probably not exactly 3. If we took enough samples, computed enough lines, we would see that we get a a normal distribution around 3. And so that kind of gives us an idea of thinking about these as a distribution, which is a little bit of a weird thing. Okay. So this is our function. Have we talked about lambda functions in Python? So we've used anonymous functions in C++ and Java and JavaScript. The Python ones are really limited. They can just have like one expression, so they're okay for something really short like this, but not good for much longer. But this is the same as just mean the same thing. So we're going to sample 1,000 data sets, each with 100 points. Okay. We're going to fit a line to each one of those. And then we're going to plot that line. And so we'll see basically 1,000 different lines fitting different data sets that come from the same distribution. Okay. The data, the true value is the y. We're going to get, so we're going to take our 3 times x, and then we're just going to add some noise. So if we plot this, takes a little while because we're doing a whole bunch of trials, a whole bunch of sampling. So these blue lines, each one is a fit for 100 data points that all come from the same distribution. As you can see, right, there's some variability in the slope and the intercept, right, because the data varies. And I think what we're showing here is I believe these are, the blue points are just one example set of points. So here is the histogram of the slopes. So these are the, for each of the trials we got a slope, a slightly different slope. And as you can see, they're distributed around 3, which is what we expect because that's, what we use to generate the data. And it looks, sort of vaguely Gaussian. Looks kind of like normal distribution, right? And so this is kind of where we get the, this is how you can understand these slopes as a distribution, right? If we got slightly different data, we get a slightly different slope, right? And we expect if we did this enough times, we'd expect to get a nice normal distribution of slopes around the true slope coming from our data. Okay. So if we look at the intercept, I'm not collecting it here, but if we looked at the distribution of the beta zeros, let's go ahead and add that. Let's take a look at what these are. So we expect this to be, right, there was no intercept in our data, right, so we expect this to be 0, and we'll see we get a histogram centered at 0. Right, so in our hypothesis, if our hypothesis is that the intercept should be 0, we won't be able to reject that. Right? We can't confirm that it's 0, but we can't say that it's definitely not 0 or probably not 0. Cool. So does that kind of make sense? I know it's kind of a weird way of thinking about this. We think about like fitting a line and that's the end of it. But really the line is kind of a sampled line from all of the possible lines we could get for all of the slightly different variations in our data. And so if we think about it kind of probabilistically, we can apply the hypothesis testing stuff to the line coefficients. So this is for TV. See how stuff works for radio. So for radio, we actually get a smaller R squared. Oh, sorry, that's newspaper. Radio, we get a really small R squared, only 0.3. But our p-value is still very small, so it still seems like there is some relationship. But the radio doesn't explain all of the variance in the sales as well. If we look at the newspaper, we have a really small R squared, 0.05. And if you remember, the newspaper was kind of all over the map. It didn't look like there was a clear linear relationship, and the R squared value confirms that, right? It's really small. Our p-value is still pretty low, but the coefficient is like really, really small, and it doesn't explain very much much of the variation in our data. So if we plot all these lines together, we get, so we see that the radio is steep, but again, it doesn't explain a lot of the variation because there's really a lot of spread here. The newspaper is pretty much useless. The TV explains a lot of the variation. So, what conclusions as an advertising executive would you make at this point? Whereas advertising does seem to increase sales regardless of the medium. Yeah. What else? So I think somebody said earlier that radio seems to be the best bang for your buck. Do we still think that?
Yes, your results may vary.
Yeah, yes, but there's high variability. Mm-hmm. How about TV?
It's most consistent, but also quite expensive.
Yeah, it's consistent, but it's expensive, and you don't get as much bang for your buck. Cool. So now we can add some more quantification to all these things that we kind of thought from just looking at the graph. But we have, we can be a lot more confident in what we have to say.
For newspaper, you said that there was a pretty low p-value, but 4 R squared value. I have trouble parsing exactly what that means.
So a p-value of 0 means there is definitely some linear relationship between these things. Its p-value is 0.001. So like there is some relationship, but this tells us it's not all that useful. Like it doesn't explain much of the variation in the data.
So I guess it feels like the R squared value is like the relationship is not valuable. But there is one. Maybe I don't understand.
So this is saying that if you increase the amount you spend on newspaper advertising, there is going to be some increase in sales, probably. This kind of tells you, but there's a whole bunch of variation within that, maybe.
What would be an example of like a high R squared that did not have a
So if you had so this is telling you the probability that that the coefficient is non-zero. So if the coefficient were actually, you could have a really high R squared if you had a perfectly flat line. So, yeah. So if the slope were actually 0, you'd have a high p-value and a high R squared value. Yeah. You could maybe think of this R squared telling you how much spread there is, and the p-value telling you whether or not it's flat. So yeah, so radio is the most biggest bang for your buck, but there's a lot of variation, so a lot of high variability. So what we actually might want to look at is considering all of these things at once, which we haven't talked about yet. We'll talk about this more tomorrow, but all this stuff we talked about for linear regression with 2 variables works for many variables with basically no changes. So we can actually do the same modeling stuff. We can throw in all of these terms, compute a beta for each term, and do this all in one shot.
And that would be like an aggregate. If you advertise, this is an idea of just being.
So this says,
across all media.
if you advertise this much in newspaper, this much in radio, this much in TV, this is what you can expect your sales to be. So you need to input your advertising budget for each thing, and then it considers all of them together. So so we're assuming that sales is a linear function of all these things. When I say linear, what I mean is that the betas are just multiplying something. So the betas, they can't show up like, the betas can't be squared, they can't show up in a square root, they can't show up in a sign or anything like that. They have to just be multiplying stuff. Okay. So with the stats models, it looks like this. Again, we use the names of the data frame, or the names of the columns here. And if we do this, we get a high R squared value. So this model explains most of the variation in our data better than any of the things did individually. As you add more terms, just based on how math works, your R squared value will continue to increase. Right? As you add more terms, they will explain more of the variation, period. So I mean, this is not a surprise. What's interesting is like, how much does it increase the R squared value by, not does it increase it. Here we look at our p-values, and we see something interesting here, which is that our newspaper has a very high p-value, which means that there is a there's a good possibility that the relationship between newspaper and sales, when you consider the other factors, is actually negligible. And so this coefficient could very well be 0. So if you look at the range of possible values, it's from like negative 0.01 to 0.01. Right? There's a good chance that it is actually 0. There is no relationship between newspaper and sales. So why would we have seen that before? Right? When we looked at just newspaper, there was a little bit of relationship. Yeah, so if you spend more on newspaper, your sales did go up, but what else? Were we not taking account of? If you spend more on newspapers, well, you also probably spent more on the other things. So I spent more on newspaper, but I also spent more on TV. The increase in sales was due to my TV ads, right? Now that I'm considering that, I can see that really it's the TV that's making the difference, or the radio that's making the difference, not the newspaper. So there was a correlation between my independent variables. There was a correlation between my newspaper and TV or radio advertising budget that I wasn't considering before. now that I'm looking at everything, I can see that, yeah, the newspaper itself isn't really making a difference. And so here we see that, yeah, so there's definitely relationship between spending more on TV and radio and selling more stuff. There may not be, newspaper may not get you anything. Yeah.
So this feels like an emerging property, but if we're putting individual dollars to each of those three, it doesn't make intuitive sense to me. The newspaper just stops being connected at all. Like, if you were to use this model and plug in a 0 for your TV and 0 for your radio, that's a value for newspaper. Why is that different than just looking at newspaper?
Yeah, that's a good question. So the issue is we don't have any data where that happened. So we really, yeah, if we kind of, we would be extrapolating if we basically tried to do that. So all of the data that we have that we've trained this model on, there was, you know, as you spent more on any, you spent more on all. And so we, to confirm whether that is true or not, you'd have to actually sample data where that happened. So yeah, it's kind of an interesting thing. So from here, if I were, you know, if I were an ad executive or whatever, I would say maybe we should try a couple of campaigns where we don't use any newspaper advertising at all and see what happens. Because what we have here seems to suggest that it wouldn't be helpful, but once you add those to the data set, then things may change. Yeah. So the newspaper is a confounding variable, right? Because when you just look at newspaper, there seems to be a relationship, but really it was probably an indirect relationship between the other advertising methods and sales that we didn't see right away. So here we're looking at, so these are the correlations between the various variables, and you see that the newspaper and TV and radio, there's not that much correlation. Some. If you look here, there seems to be a pretty strong correlation between the radio and newspaper. So it seems like maybe when we were, so the TV seems to be not that closely related, but the radio and newspaper budgets seem to be at least somewhat related. I think that's kind of less obvious from looking at the plot here, but the correlation of 0.35 is not super high, but cool. So knowing that, we might change our model, say, okay, well, screw it. Let's throw a newspaper out, and we won't use it in our prediction. So we'll make a new model that's just looking at TV and radio. It's a simpler model. We'll see what we can do with the 2D model that we couldn't do with the 3D model in a second. So now we just do TV and radio. Our R-squared value went down a little bit. So it was, see, before it was 0.897. Now it's 0.8, oh, stay the same, 0.897. Right, so the our new model explains almost exactly as much of the variation as our old model did. If we went out to a couple more sig figs, this would be slightly lower R-squared, but so this model is as good as the other one in terms of the R-squared value. We see all of our coefficients have really low p-values, meaning they're all important. Yeah. Cool. So, and now that we have a simpler model, we can actually plot it in 3D. So this is a plot of our radio and TV budget. And this plane is the equation we fit. So in 2D, the linear equation is a line. In 3D, it's a plane. And so we're fitting a plane through the data. And we can actually see that here because we have this one doesn't seem to rotate. Oh, you can change your point of view programmatically. I think there's a way to do some interaction in these notebooks, but 3D plotting is kind of a big pain. So, like, this is the one line it takes to draw the points. This is the 6 lines it takes to draw the plane. And, so yeah, we have this relationship here. So that was an example of a multilinear relationship. We had linear relationships between multiple variables. We had more than 2 betas. We can also do, we can do basically whatever we want with ordinary least squares, as long as the betas are only multiplying things. Okay? So for example, if we wanted to look at this more complicated model where we have a third coefficient for TV times radio, which we think maybe is important for some reason, we can do that with ordinary least squares. None of the math changes. We look here, our R squared score jumped up by 7%. That's pretty good. We see that the TV times radio the p-value is 0, so there is some linear relationship between sales and TV times radio. We have an even more accurate model because we included this nonlinear relationship stuff. So if we plot this, it's hard to see here, but this is no longer a plane. There's actually some curve. So as we multiply the TV and radio, there's a little bit of a curve up. So the more terms we add, the higher our R-squared value is going to be always. Okay? So kind of like p-hacking, you can get whatever R-squared value you want by adding more terms, but that doesn't mean your model is better. Okay? By looking at the p-values of the individual terms, we can see whether or not there is actually a non-zero relationship between things. And so we can simplify our models. We're trying to balance the simplicity and the predictive power of our models when we're trying to choose between them. All right. Any other questions on this? Yeah.
I guess I'm a little bit done on the hypothesis testing. I think we're looking for small values, and here it seems like the bigger values.
So a small p-value means you can reject your null hypothesis. In this case, our null hypothesis is the coefficient true value is 0. And so a small p-value means we can reject that and say that the coefficient is non-zero. So we've set it up so that we reject the thing that we don't want to be true. So yeah, it is. We're doing the same thing here. Our null hypothesis, the thing we're trying to reject is the coefficient should be 0. So if our p-value is larger, then there is a reasonable chance that the coefficient truly is 0 and there is no relationship between for that one. Any other questions? Yeah.
So if we have higher RSS, I guess we have better fit of the model and the data.
So a high RSS, yes, that would mean that there is there's a big distance between our model and our data. The RSS is a little bit misleading because it's not normalized, right? So it could just be dependent on the scale, which is why we do the normalization to get the R-squared value. So the RSS is just the absolute squared distance between our points and our line. And the R-squared is just normalizing that so it's between 0 and 1.
So I guess lower value will suggest better fit.
So a lower RSS would mean that our points are closer to the line.
Yes.
And when we convert that to the R-squared value, the lower the RSS, the closer the R-squared value will be to 1.
But in that case, if we add terms, we will introduce more deviation from on.
No, if we add more terms, we will never get worse, right? So if we added a new term and there was no relationship, the least squares would pick the coefficient to be 0. So there's no way we will add more error. We can only reduce that error, right? Because if we would add more error, the coefficient would just be set to 0. Right? So we always decrease. Right? We always pick a coefficient that removes a little bit more error. But that doesn't mean it's a better model. So we'll talk more about that, about sort of model selection stuff tomorrow. Any other questions? Cool. I'll finish a little bit early today then, I guess. Keep an eye out for the next homework. It'll be up. We'll put that up in the next hour or so. And I will see you tomorrow. We got another double dose of data analysis and viz, and then we'll be back on Thursday.